Hey everyone, this is Matt with Learn Everything About Design, and in today's video, we're going to go through an example or a part of a project in CAM. Now, CAM is computer-aided manufacturing. We're going to look at doing a 2.5-axis project. We'll talk a little bit about that, and I'm going to highlight the course that we just created or we just released on our learneverythingaboutdesign.com website. So in this video, if you don't know what CAM is or you're just trying to get started and understand the basics of it, this video will probably help you, give you some of those nuanced basics. If you are looking to learn a bit more, I would suggest checking out our course. I will put a discount code in the description of this video. There'll be a limited number, but it's a lot. And so if you're looking to get a little discount, check out the description of our video and I'll put that in there, as well as a link to our website. But we have a lot of courses here. We do have one course on Quick Surface Pro. We're working on more. There are some advanced courses in here for things like surface modeling forms. We've got one plasticity course. I'm working on more for those as well. And lots of different CAD courses. Everything from our game controller design, which is PCB, picking out parts, Arduino programming, and designing housing for 3D printing. We design the same housing injection molding, a beginner's guide to 3D printing, and so on. So definitely check these out. There are some bundled courses. So some of them are relatively inexpensive. So for example, $10 for the Absolute Beginner's Guide to CAD. And then if you bundle all of the Absolute Beginner series together, I think it's like 35 bucks. So if you are looking to learn Fusion, especially if you're looking to learn CAM, I would suggest checking this out and see if it fits. So the CAM course is going to go through quite a lot. So we start out with the basics with 2-axis cutting. This is a preview lesson, so you can watch it for free. You can check it out and see if you like the style of it. There is also a preview lesson for 2.5-axis sample setup 1, which is kind of what we're going to be going through in this video. And then there are lessons for 3-axis, lessons for multi-axis, and the conclusion. So if you are looking to get started and you want to learn more about the process, we do go through several examples. I'll show them now. And then we'll kind of talk about this one a little bit. So our 2-axis example, 2-axis is essentially a 2D cut, meaning that the tool only moves in the X and Y axes. Now this isn't 100% accurate because most of the advanced tools now will have a tilting head and you can do some pretty complex cuts with them. But for our purposes, a 2-axis part is going to be something like a sheet metal part that's getting cut with water jet, laser cutter, a CNC plasma cutter, that kind of thing. When we move into 2.5 axes, these parts are typically parts that will have the tool enter in the Z direction, so a standard 3-axis mill, but the tool is only going to move in 2 axes. So for example, facing the top of the part, it moves back and forth in X and Y. When we're clearing out stock, the tool comes down in the Z direction with a helical entry into these pockets, and then it moves in X and Y to clear out material. So these 2.5-axis style tool paths are typically the starting point when learning to program a CNC mill. Now, the reason they're a starting point is because you can kind of isolate what the tool is doing. And these 2D tool paths, it's 2.5 axis, but these 2D tool paths are done based on face or edge selections, typically called chains. Now, the difference when we get into a 3-axis part is typically the tool can move in X, Y, and Z at the same time. Now in X, Y, and Z, this means that as the tool is coming down, it is able to move in all 3 of those directions. And typically we see this more with a finishing tool path. So for example, if we're trying to finish off this complex area, the tool can move in X, Y, and Z as it needs to machine that geometry. And so when we think of a 3D tool path, we are thinking more about the tool moving simultaneously in those 3 axes. But from the toolpath standpoint, what we're actually talking about is the toolpaths are model aware. With our 2D or 2.5-axis toolpaths, we are clicking on faces, we're clicking on edges, and that's how we're defining the geometry. On the 3D toolpaths, we typically give it an area to machine. We'll restrict it to a face if we need to, or a sketch boundary or a silhouette or something like that. And then it'll use the actual geometry to generate the toolpaths. We also have a couple of sections on multi-axis machining. Keep in mind with multi-axis machining, if you are going past the 2D or 2-axis unwrap, which is basically an axis substitution, or if you're going past multi-axis positioning, then you'll need the manufacturing extension. The multi-axis toolpaths, as well as some other modification toolpaths and hole recognition, these are inside of the extension. So if you're a hobby user, this is a bit different because hobby users will have restrictions. They won't have access to extensions. And they also won't have certain functionalities such as tool changes available to them. So if you're looking to learn this, I would suggest focusing on commercial users or hobby users that have EDU users that have full functionality in the CAM workspace. However, if you are trying to learn and you want to see if this is something you need, you will be able to do some of what we do in the course with a hobby license. But again, there are going to be some restrictions around things like tool changes and posting and outputs and things like that. So with all that said, I'm not going to just play the video that we have for setup 1 from the course. Again, that is public. So if you have access to this website, you can sign up for free. Any of the lessons that are preview, you'll be able to click on those and you'll be able to get the information in here and you can watch through. What we're going to do instead is I'm going to walk through the toolpaths that I've already created, and then I'm going to walk through the process of creating a toolpath on your own. And the reason for this is because, again, the information is already there for you. If you want to go check it out, you can watch the full video on that. But it is important that we do recognize that in the courses, we also talk about things like setting up stock, building our digital twin, which is setting up our vise and our stock and our material. And we go through the process of doing that for flipping the part over into multiple orientations. So once again, I do suggest if you are interested that you check out the course, at least the preview lessons, and go through that to see if it's something that you want to do. But for this video, let's talk about the basics of a setup as well as the toolpath creation. So typically when we are machining a part, we'll start with a couple of standard toolpaths. When you have a piece of raw stock set up on a machine, the first step is typically to face it. Now, in some instances, you may have a pre-faced or pre-machined piece of stock. This setup 1, we assume that we have a pre-machined bottom of the stock because when we flip it over, we're going to use that as our reference. In setup 2, however, we do start by facing the top of the stock, which is removing extra material on top, and then we start to clear out those additional areas. So that first step is typically facing the part, and then we go in and we start to pick out the different geometry that we need to machine and figure out which tool paths we want. Now, this is oftentimes the tricky part because there are many different tool paths we can use for various things. 2D adaptive, for example, is a special kind of tool motion that allows you to keep a consistent load on the tool, whereas a 2D pocket toolpath, which could also be used, is something that generally has a higher load on the tool in corners because it engages more material. Now, these are things that we talk about in the course and you'll learn over time as you begin machining, but for our purposes, we're going to focus on just walking through each of these toolpaths. When we're drilling holes, typically you want a nice machined surface, and then you will spot drill the hole. And again, there are rules that you follow, things about the actual tip angle of the spot drill and having that be different than the actual drill bit. And if we're tapping, then, or if we're boring holes, then there'll be certain requirements that we follow there as well. Okay, so with that basic overview out of the way, let's go ahead and we're going to create a new setup. Now, if you want to follow along, I put this data set in the description of the video. It does include both setups already there, so you can look through all the toolpaths that we created in that course, and you can simulate them and take a look at them, modify them if you want. But we're going to get started creating a new setup. Now, a setup is going to be the orientation or the position that you place your part in the machine. So every time we think of a setup, think of physically putting a piece of stock in a vise on a CNC machine. So we're going to go to our setup dropdown. We're in the manufacturer workspace. It should have automatically come into here based on the data set. But if it's not, make sure that you go to the workspace picker on the left-hand side and go to manufacturer. We're in the milling section of the tools, and we're going to go to new setup. Now, when we have a new setup, the first thing that you'll notice on the screen is the coordinate system pops up, and then the material on the part is going to have all these little white dots. Now, these are what are called box points, and they're standard locations that we can click on for the location of our coordinate system. With a standard CNC machine, we're going to have Z pointing up away from our part toward the spindle where the tool is. We're going to have X going to the right as we're standing in front of the machine, and then Y will sort of take care of itself from there. So the first thing that we need to do is we need to reset up the orientation of our coordinate system. This can be done in the WCS section of our dialog box over here. We're going to do this by z-axis / plane and x-axis. Now you can come in and you can click a plane or an axis or a face or an edge. You have all different types of selections. I'm going to click the top plane, and then I want to flip the axis so it's pointing up. X is already pointing to the right, so there's nothing else I need to do. And Y is pointing away from us. And so when you think about this, when you set up the part on the machine, as the part moves to the right, that's positive X. As it moves away from you, that's positive Y. And as the tool moves down, that's negative Z. As the tool moves up, that's positive Z. So what we're going to do also is select this box point, which is the stock point, and we're going to put this in the upper left-hand corner. Now this is a common location if you're manually setting the location of your XYZ 0, because you can use an edge finder and you can actually get the edge finder to both corners, and then you can use a tool and set Z at the top of your part. Now when you're doing this at the machine, this is a little tricky. Most new machines won't actually let the spindle spin with the doors open. If you have an older machine, then you can get around that. But it is something you do need to be careful with, and spending time on the machine or taking a class at a community college or a tech center or going through some basic training like that is going to be very important. If you're trying to do this on your own at home, many of these desktop machines will have automated coordinate system finding, depending on which machine you have. If you have to do it manually, then basically what you need to do is you need to set the coordinate system in your machine at 0 at that corner. Now there's going to be a coordinate system for the machine, and then there's going to be a coordinate system for work. And we'll talk about that in just a second. The next thing that we want to do is make sure that the model that we're using and the fixture that we're using are defined in here. And this is for a couple of reasons. But for the model, we're going to select model, and I'm going to select the part on the screen. For the fixture, I want to select my standoffs or parallels. I'm going to select the jaws of the vise, and I'll also grab these other pieces as well. Now, the reason that this is important is because this is used for collision checking or collision validation. With 2D or 2.5 axis toolpaths, there is not going to be any automated collision avoidance that we can use, but if we're simulating and the tool happens to hit these, then we'll be able to see. Now there are some clearance values here. These clearance values are actually important because if we're trying to machine a pocket down into the part and the tool gets within 0.2 inches of that, that will trigger a collision. So that's something that you want to keep in mind. If there are problems, you can always come back and adjust those numbers. The second tab is going to be stock. Now, we actually used stock box point, and because I already have setups in here, we've got from preceding setup. And so what this does, that actually carries the stock from previous setups we've already created. That's not what we want for our specific instance because we're assuming we're starting new. So what we're going to do is select from solid. Now, from solid is typically what I do because I like to go in and actually model the stock. So in the bodies folder here, I've got a body called stock. It's unselectable and the opacity is turned down, but that way I can just select this as my stock body. You will want to double check that your WCS box point for the coordinate system did go back to that upper left-hand corner. It should have automatically done it, but if it didn't, make sure you reset that so that it's correct. There are other ways that you can define the stock. You can do it relative to the part. So for example, you can say relative size box and give it some offset. The reason that we don't do that, or I typically avoid that, is because I find it easier for us to generate or decide on the stock size beforehand. So if you're purchasing raw material or you have to cut it on a chop saw or bandsaw or something like that, then you need to know exactly what size each of those pieces is. And I find it easier personally for me to pre-model that and then to set the stock as unselectable, so I'm not always clicking on those faces, and then change its opacity. Now, if we show it, it really doesn't look very different than when it's hidden. And again, it's because I've got the opacity fairly low so we can see through it. The last tab here is called Post Process. Now, this is where we define things like the program number or a comment if you want to put those in. But really the important thing here is the WCS offset. Now, by default, this is going to be set to 0, and in most cases, the post processor, which is the bit of information that translates our toolpaths to machine readable code, that is going to take this and use the default lowest or next available coordinate system. For a lot of controllers or a lot of machines on the market, 0 or 1 is going to represent G54. 2 is going to represent G55, 3, G56, and so on. You will need to double check your specific controllers. And also, back on the Setup tab, there is a machine selection option. This allows you to pick through a library of machines. And if you pick a specific machine, let's say a Haas machine, then this is going to display as 54, 55, 56 instead of 0, 1, 2, 3. So picking a machine can be helpful. There are other properties that come with the machine. So for example, if you have a travel limit, an X and Y travel limit, or a spindle speed restriction, those can be baked into that machine definition, and then they can also prompt you with warnings or errors when you're trying to create your toolpaths. It'll tell you that the RPM exceeds the available limit. There are other settings in there that are important when you get into multi-axis as well, but it can be very handy to select a machine, but for our first example, we're not going to do that. So we're going to say OK, and now we've created a new setup called Setup 3. I'm going to click on this again, and I'm just going to call this YT for YouTube setup. And now we've got a new setup. It's active. So the green, the little dot next to it means that we've activated this. It happens by default. And then we are going to start to define our toolpaths. This design should already have a tool library associated with it. When you go into Manage and into the library, when this opens up, you'll see that there is a document section at the very top and that there is a 2D sample. And then it'll list the tools that are in Setup 1, Setup 2, and then now in this YT setup. We haven't used any tools yet, but all the tools that are in Setup 1 and Setup 2 are ones that we can use. All right. So what we're going to do now is we're going to close this because we're not defining any of our own tools. We're going to close that and we're going to start to actually create some toolpaths. Even though it's not needed, I'm going to go ahead and start with a 2D facing operation. The first thing that we want to do is select a tool. Now I'm going to go in and I want to select the 1/2-inch flat end mill, which is tool number 7. So we're going to select tool number 7. I'll use its default preset value, which is 5,000 RPM, a cutting feed rate of about 40 inches a minute, and we'll select it. From here, the second tab is called multi-axis. It's not one that we're going to use. The third tab is geometry. By default, with a facing toolpath, you'll get an orange border on the part. Now this is the stock selection or the stock contour. It automatically knows the size of the stock from our definition in our setup. So for this toolpath, unless you need something specific, you don't have to make a selection. The next tab is the heights. The heights are going to define a couple of different things. When we look at this from the side, and I'll zoom in a little bit, we've got a plane at the very top, which is our clearance height. Then we've got a next plane, which is going to be our retract height, and the feed height, and then a bottom height. And so what happens with these different planes is the fact that it determines when your tool goes from, say, a rapid movement where it's moving incredibly fast to a feed movement, which is the speed that we dictate for engagement in the stock or in the material. You can move these planes around. You can adjust them manually on the screen. You can also manipulate how they're controlled over here. By default, for different types of toolpaths, so for example, the facing toolpath, it will default to using model top for the bottom of the toolpath. And so you'll notice in this case that the bottom and the top are both defined the same. You'll also notice as you go up, the feed height, which is where the tool changes from rapid to a feed movement, is defined by an offset value relative to the top height. So this means that if I move the top plane, that means that the feed plane is going to move as well. So as I move this up, you can kind of see that the green plane is moving with it. The bottom height here, I want to leave exactly where it was. But you can manipulate those on screen. It's a good idea when you're getting started to leave the default planes and orientations alone and double check your bottom height, which is where you're machining to. And the reason I say this is because these are relatively safe heights. And especially if you don't know how long it takes for example, your mill to change or slow down from that rapid distance or that rapid height to a feed, then you may run into issues where you actually collide if you make them too close. So again, leave them as default for now, but always double check the bottom height. And then we go to our section, which is the passes. Now in here, the passes are for a facing operation are not really that important. They're going to automatically be driven by values of our tool. So for example, pass extension, this is how far the tool is going to go past the edge of our part. Our tool is a 1/2 inch diameter, so 1/4 inch radius. It's going to extend it 0.0004, a very, very small amount past the edge of our stock. And again, this automatically comes in based on our tool. The step over value is going to be slightly over 50% of the tool, so you can see by default it's 0.35. And again, for our purposes for this, we can leave all these as default. If you have something specific that you want to change, you can play around with it. You can always come back and edit. And the last one here is linking. And this tab, you're going to find these tabs are common across pretty much every toolpath. But the linking parameters are going to determine how the tool goes into and out of the cut, essentially. So if it has to move around the part a lot, if it needs to arc into the side of the part, this is where we would control that. Different toolpaths will enable different options, but for the most part, these tabs will be consistent. So we'll say, okay, it's going to create a toolpath where it uses that tool and goes back and forth over the model. Now, if you're not seeing this on the screen, there are a couple areas that you want to identify: toolpath visibility and the stock visibility. Now, in-process stock is going to be shown as green. And so if you turn this off, that green is going to disappear. And the toolpaths will be shown by default, but you can turn those off. You can also turn on or off different sections of that. So for example, if you only want to see cutting moves, you can turn off the leads and the links. And so basically this is determining the non-cutting portion of the move where it's outside of the stock and the cutting portion. So now that we have the first toolpath down, the next thing that we're going to do is we're going to start to remove material from the inside of this pocket. Now, if we take our measure tool and we inspect the radius value here, you can see the radius is 0.3, the diameter is 0.6. I made this part specifically larger than that 1/2 inch end mill so it could be used. That's generally not the case. Usually you'll have to come in with a smaller end mill to finish those parts off. But for our purposes, we're going to go through some common tools and common toolpaths. So first thing, 2D adaptive clearing. Now this is a very good tool path to use to clear out material, especially on these internal areas, because again, it has a specific type of tool motion called a trochoidal motion that allows it to keep a consistent load on the tool. And this is important because you don't want the tool to spike in load really high and then drop low. And you'll find that this happens when you use a toolpath like a pocket or a contour, where it's cutting and it goes into a corner and then it turns around and it suddenly has about half of the tool is embedded in the stock, which really ramps up the load. And it affects things like the accuracy of your cut, the quality of the cut. You might get chatter, or you may have some chips that get stuck between the tool and the sidewall. So typically I'll go to an adaptive clearing first for a 2D part. And for a 3D part, I'll use a 3D adaptive clearing because it can step down and step back up, and it gives us a really efficient cut. So 2D adaptive clearing, it's going to automatically use the last tool that we had selected, which is that 1/2 inch flat end mill. That's the one that we're going to use. Then we'll move on to our geometry tab. And again, when we're talking about 2D or 2.5 axis toolpaths, these are going to be based on geometry selections, whether it's a chain or a face of the pocket or some other selection option. There's a drop down here that shows you the various options. So sketch profile, silhouette, pocket recognition, we've got pockets, face contours, and chains. And there are nuanced differences to why you would select some over the other. So if I select this face, for example, you'll notice that the blue highlight happens for the face. We've got a lighter blue line around the outside, which is our chain. And then we've got these openings in the middle. Now the openings, or those blind holes, are treated as open pockets. So if we pre-drilled them, it would assume that we're not machining them. If I just say okay and generate this toolpath, what ends up happening in some cases is it'll start to avoid those. So if the tool is smaller than that hole, it'll start to go around them. So typically what I would do with geometry like this is if I know that it's not an island or geometry that's coming up, what I would do is select the bottom edge. And then you can see it's highlighted over, it's that blue color over top of those holes. And so what this tells me is that it's treating it as if those holes don't exist. Now it will generally create a different toolpath based on those two different selections. And so it's really hard to tell. And if I turn the stock off, which is F8 on the keyboard, if I turn the stock off, you can see it's just going right over that hole. If I select the face instead, where it thinks that that hole is there, it actually does change it slightly. But again, our tool is larger than the hole. So in this case, it's going to produce very similar results. But just as a general rule of thumb, if you want to machine over those holes, then you can select that edge. Now, one of the updates that happened in this month, November, for Fusion is the ability to machine over holes in 3D automatically without having to create extra geometry. It doesn't really apply to 2D because it's still very much based on our selection here. But in 3D, that is a very nice option. All right, so the next thing that we want to do, again, double check our heights. The bottom height now is based on our selected contour. And that's important because if you happen to, say, select this upper edge, it's only going to machine down to that top face. It doesn't know that it needs to go down that far. You can override this by changing this to selection, for example, and getting it to go all the way down to that face. But in general, it's better for you to select the geometry that you're cutting. Now, there are exceptions to this. So, for example, if there was a fillet in that lower corner, we wouldn't be able to select the appropriate contour on the bottom because it would be inside of the actual pocket. So we have to select one on the upper edge and then, kind of dictate where that goes. But for the most part, if you can, make sure that you select the bottom edge or the bottom face. For our passes, this is where we want to pay attention to the settings. Stock to leave. A 2D adaptive is not a finishing toolpath. So we always want to leave a little bit of stock behind. And this is because it's really meant to go in and just hog material out and get rid of that most amount of material as efficiently as possible. So make sure that stock to leave is on. You can change the number up or down as you want. The other thing that we want to pay attention to is going to be the optimal load. Now the optimal load in this case is 0.2 inches. And if you hover over this with tooltips on, you'll get a preview of what this means. But essentially, the optimal load is going to be the amount of engagement that we have on our tool. Remember, it's a 1/2 inch tool. And so what we're saying is we want to engage slightly less than half of that. So the radius of the tool, but slightly less than that. So we're not driving through the center rotation axis of the tool. And last thing is linking. And so the main thing that we want to look at here, again, we've got more options than we did with the face tool, is that the type of entry here by default is helix. So this means that the tool is going to come down from Z and kind of spin around as it gets into the final height, and then it'll move around. So we're going to say OK, allow it to generate that tool path again. I'm going to turn F8 on, which is my in-process stock. And you can see that we've created that pocket, and you can see there's a little bit of material left at 0.02 inches. And that's on both the sidewalls as well as the bottom. So this means we now need to go back and we need to finish it off. A good finishing toolpath for this is a 2D pocket. And this is because it can create a contour around the outside, but it can also create a toolpath to completely machine that bottom face. So again, for geometry, I'm going to select that bottom edge. And then in our heights, make sure it goes all the way to the bottom. And then in our passes, we're going to disable stock to leave. Now, there are plenty of other options in here that you can explore, things like multiple depths or finishing passes, or if you want it to do, multiple cuts, you can have it do that. For our purposes, we just need it to come in once, go around the outside, the bottom and the outside, and then it'll be done. So you can see it does that helical entry. Because the pocket is bigger than the tool, it does a pass here, and then there's this sort of green squiggly line that happens. That's one of those linking motions. So it moves from inside here, and then it kind of moves over, and then it does the outside cut, and then it retracts. And that's this yellow line with the green arrow on it. When it's entering the stock, because we've already removed a ton of material, it's actually spending a lot of time doing this red circular or helical motion where it's not cutting. So this is a case where you start to play around with the heights. Now, again, I don't recommend doing this getting started. I recommend you leave it. It'll mean that it's going to take longer for it to actually cut because it's spending extra time. But what we can do as you become more advanced is you can say, all right, well, instead of the stock top, I want to start my helix here, and I'm going to give it a small offset like 0.1. And so what happens is now it starts that helical entry much lower. Now you might be thinking, we set it pretty low at 0.1. Why is it still doing so much of that helix? Well, remember in the height section that it's actually starting to feed 0.2 inches above wherever we set our top height. So right now it's starting 0.3 inches above. Now if we set this offset to 0 and we set this top height to 0.1, then what we're doing, it's going to give us a warning because it's saying, hey, are you sure you know what you're doing? It's going to give us a warning. But now it's starting well below. We're going to have that warning that goes with it because of some of the parameters in the linking section. But for right now, again, for this example, don't worry about it. Just want to highlight the fact that we can play around with these values, and this will impact the amount of time we spend in non-cutting moves. For a small part like this, honestly, it's not going to make that much of a difference, a couple seconds at most. But for larger parts or more complex parts with lots of pockets, you will start to notice that you can start to save minutes or more on larger parts. All right, so now we've machined the face, which we didn't need to do, but just as an example, we've roughed out the pocket and we've finished the pocket. Now we have to take care of these holes. Now these are holes that go all the way through the part, but the other side technically hasn't been machined yet. All right, so we have to remember we need to take the tool further down. Now if we measure these, we can see that they are a 1/4 inch diameter. Now 1/4 inch diameter means that our tool is not going to fit in there. Now we can drill these out, we can create a tool path to machine them out. It just depends on your requirements for things like tolerance. Drill bits are going to have a certain range of tolerances for making holes in terms of their precision, and doing things like a 2D bore operation or a 2D contour are typically going to give you a higher level of accuracy to the CAD model. And so what we're going to do here is we're going to start by spot drilling, pre-drilling, and then we're going to do a finish mill. So the drilling tool path is going to require a specific type of tool. While it would theoretically let you use an end mill like this 1/2 inch flat, you can do that if you've got a center cutting end mill, but for us, we want to use a spot drill. Now, a spot drill is a type of drill that's really meant to come in and break through the top surface to leave a small sort of V channel, and then that will help center the drill bit. So what we're going to do is select our geometry. We're going to select both of these holes, and we'll move over to heights. Now, by default, the height is going to know where the top of the hole is, and then again, it's going to move that top height 0.2 inches above, but then it's going to automatically want to go to the hole bottom. But Fusion has a lot of different nuanced options that we can use for these hole drilling. So if we go to the drop down here, you can see that we've got to chamfer width, to chamfer diameter. We've also got just a selection. We can go to the top of the hole, the bottom of the hole, top of the fixture, bottom of the fixture. So there's a lot of different settings that we can play around with in here. I'm going to go ahead and go to chamfer diameter. And what this will do, generally, it will take the tool down all the way until the chamfer, the taper on the drill, the bit that we're using, matches the diameter of the hole. Now this is great if you've got like a countersink, but for us, that may actually make the hole slightly too big on that upper edge. So what I'm going to do is take the value that it automatically pulled from our tool, and I'm going to reduce it. And so what this will do is it will keep the tool from going down that far. So I'm going to say, okay, allow it to generate. And there we go. So you can see that it's the size of the hole is here, and it's taking that spot drill. It's kind of hard to see, but it's taking that spot drill into the part, but it's not going all the way out to that full diameter because we changed that value. Now we want to drill those holes. Instead of creating another drilling operation, what I'm going to do is right click on this, and we've got two options. We can duplicate it, which will create an exact copy. Then we go back and we modify the parameters, or we can create what's called a derived operation. Now, derived operation allows us to create additional toolpaths, drilling or milling, that will inherit the settings that we used in this one. Now, in this case, for our drill, it's going to inherit the tool that we had, the selection for our holes, and some of the other settings. So what we need to do is change our tool. Now, in this case, we're going to drill. We're going to use tool number 2, which is a 118, a number 20, 118 degree on the end, number 21 drill. There's also a 1032 tap in here, but you can see that this is not the right size. It's a 1/4 inch hole, and we don't have a 1/4 inch drill bit. If you want to, you can go down into the Fusion library or the vendor library, and you can find another tool and holder. For our purposes, what we're going to do is we're going to end up just milling the hole out. So we're going to pre-drill it, and then we're going to mill it. Next, we're going to go to geometry. Holes are already selected. And then the heights, again, it inherited that chamfer width. So what we want to do is we actually want to go to the hole bottom. Now, the problem with the hole bottom is that it's not on the bottom of the part. So if we look at this from the side, this is the point where the hole ends. And the drill bit has a taper on it. So the drill bit, at the very least, needs to go down a bit further. So there's a checkbox here called drill tip through bottom, which will use the geometry of the tool, and it'll extend it down. And so this allows us to get essentially the drill bit all the way through the bottom. But honestly, that's not good enough. We generally want to add additional offset. And so in this breakthrough depth, this is a positive number. We can say, let's go another 0.2. It's quite a bit further than we need to, but we're going into material that's still there. That pocket hasn't been machined yet. So we're going to go down a bit further. The other thing that we need to do is we need to adjust what's called the cycle. Now, anytime we're spot drilling, coming down with a rapid movement, just doing a quick spot on top of the part and rapiding back out is completely fine. As we start to drill holes and get deeper, especially if we've got smaller drill bits, we need to be very careful about the cycle that we're using. So we're going to use what's called a chip breaking cycle. And what this does is it actually brings the drill bit down into the hole and then retracts it a little bit, and then it goes back into the hole and comes back out. And it does this until it gets to the bottom that we've set. Now you can modify these parameters if you want to. I'm going to leave them as default because we're not machining this. But essentially, this allows for two things. One, it allows for chips to be removed or pulled back out of the hole. It also allows coolant to get in there. Now, if you just took the drill bit down, if it's a large enough drill bit and you know the speeds in your material, it can be fine. But for the most part, as you start to drill, you're going to want to use a peck or a chip breaking type cycle. All right, so now that we've drilled those holes, the next thing that we need to do is finish the size of it. And again, I don't have an appropriate size drill bit available in the tools. And so what we're going to do is we're going to mill it. Now we can mill it a couple different ways. We've got a boring toolpath, which is basically a continuous helical ramp as it goes down. We can also do a 2D contour toolpath, and we can drive the 2D contour using a helical entry or a ramp based on those settings. And either would be fine. We're going to look at the bore in this case because it's more applicable. But again, 2D contour, we could kind of tweak and get very similar results for this example. So for the bore toolpath, we need to select a tool. So we're going to go to the 2D samples. We've got a 3/16 flat end mill. Remember, it's a 1/4 inch hole. So 3/16 flat end mill. If we look over here on the right-hand side, you can see that this is a standard Cat 40 ER collet style holder. And you can see that the tool is sticking out just below the bottom there, that sort of gold bronze color. And if we look through here, we've got length below holder, just under 3/4 of an inch. And so what we're going to do is we're going to select that tool. We're going to go to our geometry, and we're going to select these cylindrical faces. Now, one difference between this and the 2D contour is the 2D contour, you'd actually have to select the edge and not the inside faces. With cylindrical type toolpaths like a drill or a bore or a circular toolpath, these allow you to select cylindrical faces, but with other types like a pocket, a 2D contour, those really want you to select edges. All right, so now that we've got those selected, we're going to move on to our heights. Now remember, it's got some default settings. It wants to go to the whole bottom, but we want to offset that. Now, the problem with this, unlike with the drilling operation, we said to go to the whole bottom, drill tip through bottom, and then there was an extra box there that said basically the additional breakthrough depth. That was a positive value. But in general, when we use these offset values, we have to look at the coordinate system. So Z plus is pointing up, so we want a negative value. I'm going to say negative 0.1. And so that negative 0.1 will allow the tool to go further down in the negative Z direction. And again, we've got our passes settings. I'm going to leave these the same. It's going to use a 2-degree ramp angle by default. That means as it goes down, it'll go down at 2 degrees. And then our linking parameters, again, these menus all change depending on the toolpath you're using. But for the most part, they are going to be the same menus. You'll just have different options depending on your toolpath. All right. So we're going to say OK, allow it to create that toolpath. And there we go. You can see that it's bored all the way through. Our in-process stock matches here, and we're going to simulate this in just a second. As sort of an honorable mention, I want to mention that we didn't machine the outside of this because, again, I'm assuming that the stock has been machined to size. And so because the stock has been machined to size, I didn't need to face the bottom and I don't need to machine the outside. But I do want to show you a 2D contour toolpath. So what we're going to do is select 2D contour. We'll just use the same tool. I'm not going to save the toolpath. For the geometry, I'm going to select this edge because that's the outside profile. I don't have it available on the bottom. And then for the heights, I need to pick a place that I want it to go because right now it's at the top. So let's go here. Excuse me. When I've been talking for 40 minutes, I need a little water. All right, so from here, what we're going to do is say selection. Now I can't go all the way down to the vise because then I'm going to be machining into the hardened steel. So I need to pick where I want to go to. Now I could go to this point, I could go to that edge, I could select a face, and essentially it's going to move basically the point where we're going to cut down to there. Now for passes, for something like this, we would typically want to do some additional depth cuts because it's not an adaptive tool motion, which means that it's not a consistent load on the tool. So we would typically go in and we would dictate how many times we want it to step down by giving it a height. So I'm going to say only go down 0.2 inches at a time. I'm also going to make sure that stock to leave is turned off because I'll use this as a finishing cut. And I am not going to worry about roughing passes because we don't actually have stock here. But if you needed it to come in from the outside multiple times, that's what a roughing pass would be. Multiple depths is going to be in the Z direction, roughing passes in the X and Y. And then in linking parameters, we've got an option to ramp. So again, very similar to how that bore toolpath worked. I'm going to turn that off for our example. And if we don't have that on, basically what it's going to do, it'll come in from the outside of the stock, it'll go around the part, and then it'll move. So we're going to say OK. And now we've got a 2D contour around the outside of the part. And you can see because of those multiple depths, it went down 0.2, 0.2, and then it didn't have a full 0.2 inches to go down that third time, so it went down to the final depth that we set. We always have to be careful when we use things like 2D contour with stock to leave and some of those entry options. We just need to pay close attention to how much stock we have. So you can see here, it's doing a very minimal entry from the outside. That's very tiny. And if we needed to come in from further away, then we would adjust that in our linking parameters. So for example, we've got a horizontal lead-in radius, and then we've got a linear lead-in distance. And so what we're going to do is I can increase the radius of that, let's say 0.125, and I'm going to increase the distance. Let's say we want to come in from half an inch away. That's way overkill, but just so we can see a pretty noticeable difference in those motions. So it increased the radius here, so basically how the tool is coming in, and it increased that linear distance it was coming in from. So if you've got a lot of stock left over and you're doing multiple roughing passes, then you can start to play around with those to make sure it's okay. All right, aside from the warning that we have for me putting that helical height a little bit too low, basically it's mad at me for the ramping clearance. And so if we go into our, basically our settings here, we've got some safe distances, values that it's really, it's looking for in terms of how far it can be away from the part. Those are generally pretty small, 0.04. And then you can see down here in our ramp, because it's using a helical ramp, it's got a ramp clearance helix. And so basically what it's saying is that this value matches the height of our part. So if I make this smaller, like 0.05, then it won't be so mad at me with that warning. But in reality, again, what you would really want to do is just make sure that you've got an appropriate amount of distance for that tool to do its helical entry and that it's not violating any of the other settings. What Fusion will do with warnings is it'll override them. It'll tell you what it's doing, but then it'll kind of choose the safest option based on your settings. And then if it's an actual error, there are some errors that will prevent you from actually posting the code. All right, so now I've got the entire setup selected. I'm going to go to Actions and Simulate. And what this allows us to do is we used in-process stock to kind of validate the material being removed. But now what we're going to do is we're actually going to simulate this. And so what we're going to do is go down to Comparison. All these tooltips are kind of being really annoying in the latest update of Fusion. But all these tooltips here, as soon as I'm going to just move the cursor and try to move away so it doesn't block it. But colorization here, we want comparison. And so blue is going to be stock that's left behind. Green is going to match the exact model, and red means we accidentally removed too much material. We'd also see red if there was a collision with stock or with the vise or something. And then we've got some other options here, but we don't need to worry too much about those for right now. At the bottom center, this little slider is going to be our speed. So this is forward and this is backward. The play button obviously allows us to play through. The other option that we have is we can hold down the left mouse button on the screen and just kind of drag forward. And then down here, we can also click at different positions. And you'll notice every time that there is a different operation, it will change colors down here. If there happened to be a collision, it would also show up there. Notice it's telling me that there are some features are unavailable in faster simulation. There is a mode up here that says simulate faster with GPU that you can toggle on and off. Depending on the availability of your GPU, depending on what you're simulating, what the type is that you're simulating, that you might see that warning as well. But again, I'm going to kind of just play back and forth. Remember, we didn't have to face it because it was already there. This is really what we want to look at, and this is the stock removal in that first operation. So I'm going to hit play. I slowed it down, and you can see that it's starting to move into the part. And remember that this is an adaptive tool path, which keeps a consistent load on the tool. So it's kind of doing these little pecking motions, and it's going to move over to the other side and kind of do the same thing, making sure that we don't violate that 0.2 inches that we defined as our ideal setting. Now we're on the 2D pocket, which is our finishing tool path. So now everything looks green. Our spot tool path, drill all the way through. Again, it's a pecking cycle, so it's going to go down into the hole and back out. And then now we've got our boring operation. Now the boring operation is where we need to be careful because the tool is shorter and smaller. We don't have an issue here, again, because I looked at the height of the tool. But if I had taken the tool down further, the holder may have collided with stock. And now it's going to do the 2D contour on the outside. You can turn on the Toolpaths if you want. You can kind of see where it's going. And it's going to do a second one. It'll lead out, lead back in. You can speed this up at any point in time. And there we go. Now we've created toolpaths and simulated the first side of our 2-axis part. Now, keep in mind, in this video, we went a bit longer than the actual video on the course because I explained more things that we had covered in previous videos. When we talked about some of the settings and stock and creating the setup and all that. Those were done independently. And throughout the course, we set up a tool library. Again, we modeled and we set up the stock and the vise and the assemblies. So we went through all those different steps in that process where we kind of jumped ahead in this example. I'm going to go ahead and save this with the YT setup. So when you download this, I'm going to put a second download link that also includes everything that we step through here. So if you need to go and check out the toolpaths here, you can also look at those. But if you have any questions on this, leave a comment. And again, if you want to see more content on CAM, we do have our course here. So what you can do is you can go in and take a look. Again, if you're not signed up for our website, it's free. We don't spam you with anything except for when a new course comes out, or if we've got discount codes for people that have already purchased courses, then we'll send out an email and let you know that. But if you sign up, we do have a free sort of modeling tips and efficiencies course, and then any of the courses that say preview on them, you can go in and you can watch that and take a look and see if it's something that you want to do. All right, well, I think that's going to do it for this video. If you have any questions, leave them in the comments. And as always, thanks for watching. We'll see you in the next one.